dynamic future of personalized medicine. We're essentially looking at a masterclass in feature extraction and radiomics, effectively transforming static anatomical images into dynamic, highly predictive mathematical models.
Right off the bat, here's the ultimate question we're exploring today. What if we could perform a biological biopsy using just pixels? I mean, for decades, a scan was really just a picture, but today, artificial intelligence is totally bridging that gap. It's fundamentally changing how we extract value from every single scan we take, turning everyday pixels into a virtual biological biopsy. It's wild. So here's our roadmap for today. Think of it kind of like a journey onto the factory floor. We've got the digital biopsy, inside the radiomics engine, refining the biological signal, the deep learning shift, clinical impact and limitations, and finally, the future of oncology. Let's get right into it.
Starting off with Section 1, the digital biopsy. We're looking at the absolute foundational building blocks of how machines actually see human anatomy.
To truly grasp radiomics, you really have to understand its basic currency, which is the voxel. Think of a voxel as a 3D pixel, literally like a single block in Minecraft. Whether a CT scan is measuring tissue density, a PET scan is looking at metabolism, or an MRI is tracking protons, that single 3D block is the foundational unit holding a very distinct, measurable mathematical value. And this is exactly where biological limits clash with computational scale. Human physicians look at a brain scan and see macroscopic anatomical shapes, edges and contrast. But machines, they don't see a picture at all. They see a massive grid of numbers. They're reading an absolute ocean of invisible textural patterns and quantitative data that our naked human eyes simply cannot process. Which brings us to Section 2, inside the radiomics engine. How do we actually harvest that ocean of data? Let's track the life cycle. The crucial thing to remember here is that every single scan goes through a very strict 6-phase blueprint: acquisition, segmentation, extraction, selection, modeling, and finally, validation. From getting the image, to isolating the target, pulling the math, picking the best features, building the model, and then proving it actually works on unseen patients. Let's break down these initial phases. Phase 1 is really all about finding the needle in the haystack through segmentation. If we want to predict how a tumor behaves, we have to isolate it perfectly. We're increasingly using AI-driven auto-contouring to map these boundaries now, and the reason is simple. Accurate segmentation is absolutely critical. If we accidentally include healthy tissue inside that boundary, it completely corrupts our entire predictive model. Game over. Now, once we isolate that tumor, we can't just jump straight into the math. We have to clean the dirty lens in Phase 2. This involves some intense pre-processing. We normalize the intensity values so a scan from one hospital matches another. We resample the voxels so they're the exact same physical size. We apply denoising filters to remove machine scatter. And we group the data through discretization. This prep work, absolutely mandatory before extraction is even mathematically possible. Okay, Phase 3 is where the magic happens. This is where we literally translate biology into math. We take that cleaned, isolated tumor and run algorithms over it to pull hundreds of variables. We get shape metrics like sphericity, first-order statistics like skewness, and super complex spatial textures. So a single tumor suddenly yields hundreds of machine-readable variables, creating a highly unique mathematical fingerprint. We call this a feature barcode. Let's think about why this mathematical texture matters so much. Imagine comparing two scans. One looks visually smooth, and the math confirms it's highly uniform. But the other is heterogeneous. It's visually speckled and mathematically super complex. The clinical translation here is massive. That disorganized mathematical texture directly maps to aggressive tumor mutation, treatment resistance, and ultimately poor patient survival. The math is literally revealing the biological severity. Moving right along to Section 3, refining the biological signal. Because honestly, extracting thousands of features from a single tumor creates a brand new, massive headache, which is data overload. We hit what data scientists call the curse of dimensionality. Just imagine extracting over 1,000 features per patient, but you only have, say, 50 patients in your clinical study. The scale tips way too far in the wrong direction. This leads to catastrophic issues, like model overfitting, where the computer basically just memorizes random noise instead of learning the true biology. It causes data leakage and leads to a complete failure of reproducibility when you try testing it at a different hospital.
So, to filter out all this noise and uncover the true biological signal, we kind of have to act like data sculptors. We use mathematical tools like principal components analysis, or PCA, to condense overlapping features into core components. Then we bring in techniques like lasso regression to aggressively prune irrelevant feature coefficients all the way down to absolute zero. After all that intense pruning, we're left with only the golden, most robust predictive variables.
Which naturally leads us to Section 4, the deep learning shift. Once we have that pure, refined signal, how are we analyzing it?
We are right in the middle of a major paradigm shift in medical imaging. In the handcrafted era of traditional radiomics, humans explicitly defined the geometric formulas. We told the computer exactly how to calculate things like entropy or kurtosis. But with deep learning, the machine discovers the pattern itself. Neural networks process the raw pixels through convolutional layers to automatically learn highly complex, totally invisible latent features that human mathematicians never even thought to look for.
Of course, there are trade-offs here. Handcrafted features offer high interpretability because the math is completely explicit, and they work pretty well on smaller clinical datasets. But they require a ton of manual human effort to segment the images. Deep learning, on the other hand, gives us raw, autonomous power with very little human effort, but it demands massive datasets and operates as a total opaque black box. But don't worry, the future isn't about choosing one or the other. It's about hybrid models that integrate the explainability of handcrafted math with the sheer power of neural networks.
All right, Section 5, Clinical Impact and Limitations. Let's tether all this dense mathematical theory back to high-stakes reality.
So how is this actually impacting patients right now? Well, this extraction technology is already powering rapid AI auto-contouring, which saves physicians hours of planning time. It's predicting tumor control probabilities before a treatment even begins. We're generating zero-radiation synthetic CTs entirely from MRI data. And honestly, the most amazing part? It enables adaptive radiotherapy, dynamically adjusting radiation beam pathways in real time as a tumor literally shrinks during a multi-week treatment course.
But look, we do have to ground ourselves. There are intense scientific and regulatory bottlenecks preventing full autonomy here. First up is the data drought. Medical data is heavily siloed by privacy laws. Second, the standardization crisis. A scan from a Siemens machine looks mathematically different than one from a GE machine. And finally, that black box dilemma. Doctors and regulatory bodies absolutely demand explainable AI. The stakes are life and death. A doctor must understand exactly why an algorithm recommended a specific, potentially lethal dose of radiation before they ever sign off on it.
Overcoming those bottlenecks is really the defining challenge of the next decade, which brings us to our final section, the future of oncology.
The research frontier is already pushing way past single static images into complex, overlapping data layers. We're exploring delta radiomics to track real-time biological treatment response. We're moving into multi-omics to get a truly holistic picture, fusing imaging features directly with DNA profiles. And to solve that data drought we talked about, we're looking straight at federated learning, training AI models across global hospital networks simultaneously, all without sensitive patient data ever leaving its home hospital.
All of this is building toward fully automated, highly personalized care paradigms. We're talking about AI physicist assistants taking over rigorous quality assurance, massive foundation models adapting to medical physics tasks with zero prior training. Ultimately, this entire trajectory points toward real-time adaptive treatment, where autonomous radiation systems adjust instantly, guided by the patient's unique, mathematically extracted digital twin.
Feature extraction is no longer just about analyzing images. It truly is the foundational language of personalized, predictive, and autonomous medicine. So, what you should really take away from this explainer is this somewhat provocative thought. As machines get better and better at reading the invisible textures of disease, are we actually ready to fully trust the invisible mathematical language of our own biology?